Okay, so now we're going to get into a discussion of the metallic character of the elements. But first, we need to talk about what we mean by the term metals, nonmetals, and semi-metals. Okay, so metals, um, in terms of their atomic structure, they tend to have a some electrons in their valence shells, no more than three, in fact, and they tend to lose electrons and form positive ions. So, for example, aluminum will lose its three valence electrons to form the aluminum 3 plus ion. And pretty much all S block elements, with the exception of hydrogen and helium, and all D and F block elements, and some of the P block elements are metals. So when it comes to metallic character, it is actually related to atomic radius, which in turn relates to the ionization energy. And what you'll find is that in terms of metallic character, they tend to increase as you go down any group, and they tend to also increase as you go from right to left of any period. All right. So basically, you can predict which element is more metallic than which based on their relative positions in the periodic table. Now, nonmetals, on the other hand, they tend to have more than four or more electrons in their outer shell, their valence shell, and they tend to gain electrons to form negative ions. And pretty much all p block elements are nonmetals, um, with the exception of, um, well, all nonmetals are p block with the exception of hydrogen and helium, which are s block elements. And basically, in terms of the metallic character trends in the periodic table, it's opposite to metallic character trends. So therefore, going from left to right of any period, the metallic character increases, and going from bottom to top of any group, the non-metallic character increases as well. Okay, so metalloids or semi-metals, they tend to have characteristics in common with both metals and non-metals. And they basically occupy, I should say, a position in the periodic table, which is kind of in the middle, but not exactly in the middle, more to the right of the periodic table. Most periodic tables that you'll see published will have this kind of dark step line going down like this. That basically represents the line of demarcation between the metals and non-metals. And it turns out that the metalloids tend to occupy one or other of the side of that particular boundary. So silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, those would be the metalloids. All right. So as you can see, well, this is the list here of the metalloids I mentioned before. All right. I mistakenly said astatine is a metalloid. It's not. It's actually a nonmetal. In any case, what you'll find, going back to this table, is that the vast majority of elements in the periodic table are metals, right? And then the next in line in terms of the total number, proportion-wise, would be the nonmetals, and then the minority 7 would be the metalloids. Okay, so those are the metalloids. So this is basically a summary of the different trends that we discussed in this chapter. And it's important that you understand these trends, and you should be able to explain these trends based on the electronic structure of the atom. So let's look at this example. It says, in each set, indicate which is the more metallic element. And again, you need to refer to the periodic table. So based on, in the case of A, hold on, sorry. Let me get my pen function. Okay, so in the case of A, because calcium is above barium, that means that barium is more metallic. So the answer would be barium in the case of A. In the case of B, let's see, antimony and tin. Okay, so according to my periodic table, antimony is in group 5A, period 5, and tin is in group 4A, period 5. But tin is to the left of antimony. So that means that tin would be the more metallic element in this case. And then when you compare germanium to sulfur, let me see, germanium is in group 4A, sulfur is in group 6A. But the thing is, sulfur is more to the top and more to the right than germanium. So therefore, in this particular case, germanium would be the more metallic element. All right. Okay, so that basically answers that. Just a few comments about the different groups within the periodic table. The first one I want to talk about here is the noble gas. The noble gases are those elements that are located in group 8A, and they're sometimes called inert gases because they're very unreactive. In fact, in order for you to form compounds with these particular elements, some special conditions, usually high temperature, high pressure conditions, are required to make these compounds. Um, and these compounds are usually very unstable. And in fact, helium and neon are the only two elements that nobody has been able to combine them with any other elements to form compounds. All right. Okay. And then let's talk about the fact that when it comes to identifying certain metallic ions, we can use what are called flame tests. If you remember from an earlier chapter when we talked about the fact that atoms can be excited such that electrons are promoted to higher energy levels, and then when they fall back to lower energy levels to the ground state, for example, they emit radiation. In some cases, the radiation is in the form of light of a particular color. Well, this idea can be used to actually determine and identify certain elements using a flame test. So as you can see in these pictures right here, you have different ions that can, when exposed to a flame, give different colors, right? So in the case of lithium, you have this kind of pinkish red color. In the case of sodium, you get a yellow color. In case of potassium, it's blue. Calcium, it looks more reddish, orange, and so on and so forth. So we can use these to identify the presence of particular metallic ions. This doesn't work well for non-metallic ions because in the case of metals, their ionization energies tend to be relatively low, and therefore these electrons are more readily excitable by being exposed to the energy of a flame. That is not the case for non-metallic ions. Okay, some things about group 7A elements in relation to topics that we have encountered before, namely redox reactions. It turns out that group 7A elements are good oxidizing agents. In other words, they tend to, because of their high affinity of electrons, for electrons, they tend to basically react so as to get electrons from something which is a reducing agent. So here's an example of the oxidative properties of chlorine. It turns out that chlorine, when bubbled into a solution of iodide ions, which is colorless, forms chlorine or chloride ions and iodine, which is the purple stuff right here. All right. Chlorine gas or the chloride ions will end up here in the aqueous solution. And the reason why that is so is because chlorine has a greater affinity for electrons. So chlorine will oxidize or pull electrons away from the iodide ion to form the chloride ion, and iodine will be the product that will be eliminated, that would be liberated. So the iodine here is a brown substance here that is formed at the top layer right here. All right. And what happens as far as the bottom layer is concerned, this solution here is the solvent is carbon tetrachloride. And basically, carbon tetrachloride, when it dissolves iodine, it forms this purple solution that you see here. All right. So you're going to have two layers, right? You're going to have the aqueous layer, and you have this layer which is the organic layer because that's a carbon tetrachloride. So up here you'll have the displaced iodine as well as the chloride ions, but this being polar, and we're going to learn about polarity later on, will pull or this being non-polar I should say, would pull the iodine into it, and therefore you end up with this purple solution. Okay, um, elements belonging to the S block region of the periodic table, they tend to be strong reducing agents, and that's in relation to the ionization energies of these substances being very low. All right, so basically what you'll have is that all the group 1A metals and the heavier group 2A metals will displace hydrogen from water for that reason. All right, and as I said before, the low ionization energy reflects the fact that the metal will give up its electrons. In this case, the hydrogen in the water, and therefore hydrogen will be displaced in the form of hydrogen gas. So you can see that in these reactions here, the first one is potassium. If you take a small piece of potassium and add it to water, then basically you're going to see a very vigorous exothermic reaction that produces heat and energy. And that's because the electrons that is given up by the potassium will um, will be used to displace hydrogen from water. Similar thing happened here in the case of calcium. It's not as vigorous a reaction. And in the case of magnesium, it is not reactive in cold water, but if you heat it, then the reaction will take place as well, where electrons will be used to displace hydrogen from water. Okay, some other terms that I need to talk about here: the difference between acidic oxides, basic oxides, and amphoteric oxides. Acidic oxides are oxides which, when added to water, forms an acid. And these acidic oxides tend to be oxides of nonmetals. Basic oxides produces bases when they're added to water. And again, more often than not, basic oxides tend to be metallic. And then you have a special group of oxides known as amphoteric oxides, which basically can react as either an acid or a base, right? And what you'll find is that metalloids and some of the heavier metallic oxides, they tend to form amphoteric oxides. Okay, so that's basically it for this chapter. So the next chapter we're going to discuss will be chapter 9. And in chapter 9, we'll be looking at molecular structures. All right, so that's it for now.